Here we will see how the kidney goes about regulating both urine concentration and urine volume. So the kidney not only filters and cleanses the blood, but it is also responsible for maintaining proper balance of both water and electrolytes. So the kidney is therefore responsible for regulating body fluid osmotic concentrations. Because maintaining consistent osmotic concentrations of not only the blood, but of the extracellular fluid is important so that cells do not shrink or swell due to the osmotic movement or diffusion of water. To describe the osmotic concentration in the extracellular fluid and in the filtrate that's being created in the kidney, we're going to use this unit called osmolarity. And osmolarity is defined as the number of solute particles that are in 1 kilogram of water. So basically we're looking at how much of a particular solute, like glucose or sodium or something like that, is dissolved in a certain amount of water that is a certain water weight, or a certain weight of water. Typically the measurement for osmolarity is if we have a higher osmolarity, that means we have a higher solute concentration or a higher number of solute particles. The lower the osmolarity, the lower the number of solute particles or concentrations. And typically the kidney is going to maintain our fluids at both extracellular and our blood fluids at about 300 milliosmoles, which is our unit of osmolarity that we'll be referring back to. So if urine is dilute, that means that urine will have a low amount of solutes in it. And typically the kidneys are producing dilute urine if we're overhydrated, that is, if we've consumed or are retaining too much water. So when we are overhydrated, the urine tends to be very dilute, and our body will produce a very high volume of dilute urine to get rid of that excess water, and there will be little solute concentrations inside of it. That is, that urine will be mostly water, very little sodium and other electrolytes within it as well. So the question I have for you here is, would dilute urine have a high or low osmolarity? And if you said that dilute urine would have a low osmolarity, you would be correct, because that would mean that there are very little solutes being dissolved into it, or that are dissolved in it. On the other hand, if we are extremely dehydrated or even mildly dehydrated, the urine that our kidneys will produce is going to be very concentrated, which means that we're going to produce very low quantities, very low volume, but lots of solutes within it. So here again, if we looked at the osmolarity of concentrated urine, the osmolarity would be very high in concentrated urine since we have a lot of solutes dissolved in a little volume of water. So how does the kidney accomplish these two different tasks of producing both dilute urine if we're overhydrated and concentrated urine if we're dehydrated? The way that the kidney goes about this physiologically is it uses what's called a countercurrent mechanism to achieve the producing dilute or concentrated urine depending on the situation that we are in. So countercurrent flow, or a countercurrent mechanism, means that the fluid is flowing in opposite directions in two adjacent segments of the same tube. So imagine we've got two tubes roughly side by side with one another, and we've got fluid flow in that tube or in that system of pipes, and the fluid is flowing in opposite directions in those two adjacent segments of pipe. So my question here for you is, where did we see adjacent segments of the same tube in the kidney? And recall that we saw these two adjacent segments of the same tube in the nephron loop here. So the nephron loop was this U-shaped structure that dips down into the renal medulla. And those two structures, even though they're not physically touching one another, they're still in close proximity to one another. So what's going on in one tube will affect what's happening in the other tube there. And so in this way, the kidney is making good use of that countercurrent flow to physiologically alter the chemical properties of our urine and the filtrate that's coming out of it, or I should say the filtrate that's coming out of it at this point. So we see two adjacent segments of a connected tube in the nephron loop. And the nephron loops are going to really make use of two physiological concepts here. One is called the countercurrent multiplier, which is created in the nephron loop. And the countercurrent multiplier basically describes the interaction between the filtrate flow in the ascending limb and the descending limbs of the nephron loop. And we're going to see how that countercurrent multiplier comes into play to remove both water and sodium from the filtrate. The second thing that we're going to take a look at is we're going to look at the countercurrent exchange, what's called the countercurrent exchanger. And this occurs between the vasa recta and the nephron loop. So this term vasa recta here should give you the idea that what we're seeing in producing both very concentrated or very dilute urine is mostly occurring in the juxtamedullary nephrons. So we're going to spend our time here focusing on those juxtamedullary nephrons, which don't make up the bulk of the nephrons in our kidney, but they're really important for creating that very concentrated urine, especially when we're extremely dehydrated. So let's take a look at the countercurrent multiplier and exchangers. We'll start with the countercurrent multiplier first. So in order to understand what's going on here, let's take a look at the fluid concentrations within the different regions of the kidney here. And what they're showing you here in this diagram is they're showing you the fluid osmolarity of the tissue that's within different regions of the kidney. So recall that the outer region of the kidney here is the renal cortex. The deeper regions where the pyramids are is the renal medulla. And what you're seeing here is that the osmolarity or the fluid concentrations are actually increasing as you get deeper into the kidney. So in the cortex of the kidney, the fluid osmolarity concentrations are roughly 300 milliosmoles that we had talked about. But as you dive deeper into the renal pyramids and the renal medulla here, what you see is that you see the filtrate becoming much more concentrated. In fact, it can increase its concentration to about 4 times more than what we saw in the renal cortex here. So we see a maximum of about 1,200 milliosmoles in fluid concentrate, or in fluid osmolarity, I should say, at the papilla of the renal pyramids. And what they're showing you here is they've enlarged a nephron in this diagram here just to remind you of where all the nephron structures are. So remember that the renal corpuscle is largely housed within the renal cortex here. So that's where the filtration is occurring. We've got our proximal and distal convoluted tubules here. But remember that those U-shaped nephron loops actually dip down into the renal pyramids here. And so that's what gives our renal pyramids that kind of striped appearance, is because we have these rather kind of straight adjacent segments of the nephron loop, as well as the collecting ducts passing through the renal pyramids here. Okay, so what we're going to see here, kind of coming back to that idea of the countercurrent multiplier and countercurrent exchangers, we're going to see really kind of 3 things happening here. We see that the very long nephron loops of our juxtamedullary nephrons are creating an osmotic gradient down their length. That's the first thing that we're going to take a look at. That's going to be the countercurrent multiplier here. The next thing that we're going to take a look at is we're going to see that the blood vessels in the juxtamedullary nephrons, those very long, straight networks of blood vessels that are running roughly in parallel to our nephron loops, what we call the vasa recta, are preserving that gradient that's created in our nephron loops by acting as what we call countercurrent exchangers. So that's that second physiological process that we're going to take a look at. So we're going to look at the countercurrent exchangers, which are occurring in the vasa recta. And then finally, what we're going to see is that we're going to see the collecting ducts using the concentration gradient that's created in the renal medulla here to either create very dilute urine or very concentrated urine, all depending on the situation. So let's come back to this countercurrent multiplier for just a second here. So countercurrent multipliers are created in the nephron loop. And recall that we had already discussed this a little bit when we talked about the anatomy of the nephron loop. Recall that the nephron loop, being a U-shaped structure, has a descending limb which comes off of the proximal convoluted tubule. The descending limb makes a U-shaped bend, becomes the ascending limb. The ascending limb then makes its way up to the distal convoluted tubule. And what you see in the descending limb is that we see that the descending limb is permeable to water. So that is, water is able to leave the filtrate and enter the tissue within the kidney. So essentially look at it as the kidney here is reclaiming water that might otherwise be lost in the urine. So the water that's leaving the filtrate is essentially going to be recaptured by the body in the kidney. Any remaining water that's leaving the descending limb or even the collecting duct will leave the body as urine, right? So the descending limb is permeable to water, but it is not permeable to sodium, or solutes, I should say. Primarily sodium is what we're going to focus on here. So water can leave the filtrate in the descending limb, but solutes like sodium are unable to leave the filtrate in the descending limb. In the ascending limb, however, the ascending limb that's making its way up to the distal convoluted tubule, the opposite is true here. So solutes like sodium are able to leave the filtrate, but water is not able to leave the filtrate. That is, the ascending limb is impermeable to water. So I talked about this a little bit earlier, and we kind of noted that we see the movement of water and solutes in the ascending and descending limbs as opposite of one another, and that seemed like kind of a strange configuration at first, but I'm hoping here it's going to come into kind of full circle and make sense as to why these two sides of the nephron loop are permeable to water or solutes. So let's take a look at what's going on here. So if we consider filtrate flowing in the nephron loop here, the direction of the arrows here is showing the direction of filtrate flow. We see our counter current mechanism here because we've got two adjacent regions of the same interconnected tube here. So filtrate is flowing down the descending limb and up into the ascending limb. So that's our counter current mechanism here. In the descending limb here, we see that the descending limb is permeable to water, but it is not permeable to solutes like sodium. And we see that water is able to leave the descending limb by passive transport. It diffuses out. What we see in the ascending limb here is the ascending limb that makes its way up to the distal convoluted tubule actively transports or actively pumps out things like sodium chloride, but it is impermeable to water. So you notice that there is no water leaving the filtrate here in the in the ascending limb here. So what's happening is that as sodium is pumped out of the filtrate and into the space surrounding the ascending limb here, the space in the ascending limb here becomes saltier. And so because the descending limb is passing in close proximity to this relatively salty environment here, that's going to cause water to want to diffuse out of the filtrate and into the space surrounding the descending limb here. So the ascending limb is pumping salt out, using ATP to do that. That salt is filling or occupying the space around the nephron loop here, and it's causing water to be pulled or diffuse out of the descending limb here, right? Remember that sodium is always, or I should say water is always going to follow sodium. So if there's a high concentration of sodium around here, water is going to want to diffuse out of those descending limbs there. So just to kind of summarize what we see here, if you want to kind of a slightly different view of that same diagram here, salt is pumped out of the ascending limb. That increases the osmolarity or the concentration of that tissue fluid, that interstitial fluid here, which causes water to leave the descending limb that's passing in close proximity to that ascending limb here. That increases the osmolarity of the filtrate as it makes its way down the nephron loop here. So as the filtrate here starts to lose water on its journey down to this U-shaped bend, it becomes more concentrated. That is, water gets pulled out, solutes are left behind here. And so that makes the osmolarity of the filtrate start to increase as it makes this U-shaped bend and makes its way up the ascending limb here. Now, as salt is pumped out here, the osmolarity of the filtrate becomes less concentrated, or less, I should say. The osmolarity of the filtrate decreases. So water is pumped out in the descending limb, salt is pumped out in the ascending limb, which means that the body here has reclaimed the water and the salt that it needs, and anything remaining in the filtrate will leave the body as urine. So this is kind of a clever way that the kidney has built itself so that it can reclaim the proper amount of water and salt, and then anything remaining in the filtrate will become urine. So we saw that the countercurrent multiplier was created in the nephron loop. We saw that the more sodium chloride that is transported out of the ascending limb equals more water diffusing out of the descending limb. So once again, the kidney here is pulling the solutes and the water out of the filtrate that it needs. Anything that remains in that filtrate will then leave in the body, or leave the body as urine. We saw also that at the U-shaped kind of hairpin turn in the nephron loop, we saw that the filtrate in the descending limb very quickly became higher in osmolarity, became much more concentrated in terms of its solute concentrations as it made its way down the descending limb. As it made its way up the ascending limb, it became less concentrated because salt was being pulled out of it. So one thing here that I want to point out, and this is just kind of that same diagram, just with a little bit more details added to it. So as what we see here, kind of summarize what's going on here. As water and solutes are reabsorbed, the loop concentrates the filtrate and then dilutes it, because what we saw is that the nephron loop is pulling water out of the descending limb and then salt out of the ascending limb here. So the body is able to reclaim those two substances that it needs. And so if we follow once again the filtrate that is entering the nephron loop, so this would be the glomerulus here, filtrate is being produced, has an osmolarity of about 300 milliosmoles, makes its way through the proximal convoluted tubule. Finally, as it gets to the nephron loop, in that descending limb, water diffuses out of the descending limb here. So as that filtrate makes its way down the nephron loop, it slowly becomes more concentrated. That is, the osmolarity of it goes up. We see that at the hairpin turn of that nephron loop, we see that the filtrate reaches its highest concentration up to a maximum of 1200 milliosmoles at the base of the nephron loop here. So it's basically 4 times saltier than it started here, since 1200 is 4 times more than our 300 milliosmoles that we started here. So the filtrate is 4 times more concentrated than it began as. But what I want to show you here is really kind of the cool thing is happening in the ascending limb here. And what you see that at the same level of the ascending limb, so if we compare the descending and ascending limbs at the same level, we see that as salt is pulled out, the ascending limb maintains an osmolarity of the filtrate at 200 milliosmoles less than it is in a comparable region of the descending limb here. Now, this is really important because what it's telling us is that our kidney is able to produce a filtrate that is less concentrated than our body water, which is really nice because it enables us to really hang on to the water and the sodium that our body needs while really kind of producing this very dilute filtrate, this really very dilute urine, so that we're not unnecessarily secreting or eliminating a lot of sodium and water from our body, because we need that. We need those to survive. So the cool thing here is that the ascending limb is able to produce a filtrate that is much less concentrated than our body tissues. And we see that as filtrate is rising from the hairpin turn here in the nephron loop up into the ascending limb, sodium chloride is actively transported out and the filtrate becomes less concentrated. That is, its osmolarity decreases in the filtrate, but the osmolarity of this tissue fluid is still fairly high since sodium is being pumped out at this point here. So filtrate, by the time it leaves the nephron loop and enters the distal convoluted tubule, it's very dilute. So it's more dilute than the fluid that it's more dilute than the filtrate that initially came out of the blood. So that's pretty cool. That's, I think, is a really interesting part or interesting ability of the kidney to be able to create a fluid filtrate that is much lower in concentration than our tissue fluids are. So we saw the countercurrent multiplier being created in the nephron loop. We saw the filtrate starting out at 300 milliosmoles, becoming more concentrated as it made its way down the nephron loop, and then it became more dilute as it made its way up and out of the nephron loop. So that was the countercurrent multiplier. Now we'll focus on the countercurrent exchanger, and this occurs between the vasa recta, which are the blood vessels that are recollecting that water and those solutes, and the nephron loop. So basically the vasa recta are picking up the water and the solutes that are pulled out of the nephron loop so that our body can reabsorb those back into our blood. So this reabsorbs the water and solutes without undoing that countercurrent multiplier that we saw in the nephron loop. And so this helps to pull water and solutes from the interstitial fluid near the nephron loop and puts those water and solutes back into the bloodstream here. So if we take a look at a very simplified diagram of the vasa recta here, we see that the efferent arterioles that are leaving the glomerulus here will then kind of bend back and run in roughly parallel to the nephron loop here. And the vasa recta here, what they are doing is that the water that is pulled out of the fluid here is picked up by the vasa recta. The sodium that is pulled out is also picked up by the vasa recta here and returned back to systemic circulation. So the vasa recta are really just helping to recollect those water and solutes that are pulled out of the nephron loop. So the vasa recta, as I've already mentioned a few times here, preserve that countercurrent multiplier that we saw and that osmotic gradient that we saw in the nephron loop. In the left side of the vasa recta, the vasa recta are pulling sodium in and releasing water near the descending limb, and that helps to preserve the amount of water in the space that's between the vasa recta and the descending limb. So you don't see the descending limb here, but it would pass in fairly close proximity to this downward channel or this descending part of our vasa recta here. In the right side of the loop here, the vasa recta are secreting sodium and drawing water in, which means that it's helping to preserve the amount of sodium in the space near the ascending limb and the vasa recta itself. So to summarize that, the countercurrent exchanger is working because it's preserving the gradient in the medulla by really kind of preventing rapid removal of salt and water from the interstitial space. So it prevents rapid removal of salt from that interstitial space and helps remove any reabsorbed water that ends up leaving the nephron loop. And so this way, the nephron loop can still act to the sodium that's pulled out of the nephron loop in the ascending limb can still help pull water out of the descending limb of the nephron loop. So really the vasa recta is helping to keep that nephron loop doing its job of being able to pull sodium and water out of the filtrate there. So let's look briefly here at how the kidney uses these two mechanisms to form either dilute urine or highly concentrated urine. And so we're going to focus here real briefly on forming dilute urine here. Dilute urine is formed when we are overhydrated. That is when our blood and our body tissues just are holding on to too much water. So what our body is going to do to get rid of that overhydration is we're going to produce very large volumes of dilute urine. So that means that our urine will have very low osmolarity. Overhydration tends to inhibit the release of antidiuretic hormone, or ADH, from the posterior pituitary. So recall that ADH inserts aquaporins into the collecting ducts. So if we don't have a lot of ADH circulating in our blood, we're going to have very few aquaporins being inserted into the collecting duct, which means that as filtrate is making its way out of the collecting duct, there's not going to be a lot of water pulled out of it. So we've already pulled a lot of sodium out of it in the nephron loop, but any water that's remaining in the collecting duct will be very dilute. Like that is, it's not going to have a lot of solutes in it. It's going to be large volumes of it, and our urine concentration is going to be somewhere around that 100 milliosmoles that we talked about. So this is a very dilute, large volume of urine that our kidney is going to produce during overhydration here. And if you want a little graphic summary of that, or a little diagram summarizing that, we see that the collecting ducts use the gradients created in the nephron loop to help produce very dilute urine here. So if we were very overhydrated, we had very little antidiuretic hormone, that means that the osmolarity of our extracellular fluids is going to be very low because we have a lot of water, which means that large volume of water is going to dilute whatever solutes are there. So we're going to have a very low osmolarity there. That's going to inhibit ADH release from our posterior pituitary, which is going to feed back to reduce the number of water diffusion channels called aquaporins in the collecting duct, which means that as water passes through, or as filtrate, I should say, passes through the collecting duct here, not a whole lot of water is going to be reabsorbed from it. And so we're going to produce this very large volume of extremely dilute urine. If we wanted to form very concentrated urine, on the other hand, we would have to be very dehydrated or fairly well dehydrated. So when we are dehydrated, we produce very small volumes of extremely concentrated urine. And when we're dehydrated, this means that our posterior pituitary is going to release a lot of antidiuretic hormone, or ADH. So the more dehydrated we are, the more ADH our posterior pituitary is going to release. Did I say anterior pituitary? I meant posterior pituitary if I said anterior pituitary. Okay. So dehydration, we will produce small volumes of very concentrated urine. So that means that our urine will have a very high osmolarity. This dehydration influences the amount of ADH that's released. So for the more dehydrated we are, the more ADH we're going to be releasing from our posterior pituitary. That high volume of ADH is going to cause many of those aquaporins, those water channels, to be inserted into our collecting ducts within the renal pyramids, and that those aquaporins are going to help pull a lot of that water out of the filtrate. And that means that our urine concentration is going to increase. That is, we're going to have a very high osmolarity in our urine, up to about up to a maximum of 1,200 milliosmoles. So again, in diagrammatic form here, we see that if we were extremely dehydrated, that we had a lot of ADH being released from our posterior pituitary. That dehydration increases the osmolarity of our extracellular fluids, because we've still got the salts and the solutes in our tissues and our extracellular fluids and in our blood, but we don't have a lot of water because we're losing it all to the environment, or we're sweating, or we just haven't drank a lot of water in a long period of time. So the osmolarity of our fluids is going to increase. That's going to cause ADH release from our posterior pituitary. That increases the number of aquaporins that are present in our collecting duct here. And that's going to help pull a lot of water out of the filtrate as it passes through the collecting duct. And so therefore we're going to produce a very small volume, but a very highly concentrated urine at about a maximum of 1,200 milliosmoles. So that's how our kidney uses the concentration gradients created in the nephron loop to produce very dilute or very concentrated urine, depending on the situation here. So let's finish up by looking at diuretics here. So diuretics are substances that enhance urinary output. These substances really come in a variety of things. So alcohol is a diuretic because it inhibits the secretion of antidiuretic hormone. So even if we're dehydrated, alcohol inhibits the release of ADH from our posterior pituitary, which means that the aquaporins that are in the collecting duct this means that there's going to be very few aquaporins inserted into our collecting ducts. And even if we're dehydrated, alcohol will still cause us to produce large volumes of very dilute urine. So it's very easy to become dehydrated with enough alcohol consumption. Caffeine and certain hypertension drugs work by inhibiting the reabsorption of sodium. So remember that in our filtrate, as sodium is passing through the renal tubules, sodium is being reabsorbed by the renal tubules. If sodium, and when we reabsorb sodium, water is following it passively. So remember that water and sodium, water is sodium's BFF. So water will follow sodium wherever it goes. So caffeine and hypertension drugs inhibit the reabsorption of sodium, which means sodium is staying in the filtrate. Water is also going to stay in the filtrate. So we're going to really decrease our fluid and blood volume here. In the case of hypertension, this works really well because if we're eliminating a lot of blood and fluid volume here, that means that our blood pressure is going to go down because our blood volume is going down. Other conditions like diabetes mellitus can act essentially as a diuretic because with diabetes mellitus, we see a lot of glucose being lost in the urine. So high glucose concentrations in the urine essentially does the same thing as if sodium were to remain in the urine. So if we have a high concentration of glucose in the urine, that pulls water out of the body and into the filtrate. And so therefore if in someone with diabetes mellitus, they would be losing a lot of glucose to their urine, but they would also be losing a lot of water to their urine as well. So in this case, glucose is referred to as an osmotic diuretic because it's drawing water from the body and putting it into the filtrate.